Welcome back to the Deep Dive. Today we're diving deep into multi-agent coordination across diverse applications. A survey.
That's a mouthful, but a really important topic.
It is. This paper by Sun, Yang, and their team basically lays out how to get multiple AI agents to work together smoothly across a whole bunch of fields, like a master key for AI teamwork.
Exactly. What's really cool is that this paper goes beyond just surface level stuff. It gets into the nitty-gritty of multi-agent coordination. What are the real challenges? What algorithms are we using? Where is this all headed?
So, for anyone tuning in for the first minute, give us the quick and dirty. What are the big takeaways here?
Well, imagine a world where AI agents can team up seamlessly. Think expert surgeons doing a complex operation or a swarm of robots on a search and rescue mission. This paper shows us how to get there.
Okay, so we're talking serious AI teamwork. But where do we even begin?
Well, you got to start with the basics. The paper defines multi-agent systems where multiple independent decision makers, called agents, interact.
Okay, so a bunch of AI agents working together.
Right. And then there's coordination, which is basically how you manage those interactions so the whole system runs smoothly and gets the job done, even if some agents have conflicting goals.
So it's like conducting an orchestra, right? Each musician has their part, but the conductor keeps everyone in sync.
Exactly. But coordinating AI agents is way more complex than leading an orchestra.
I can imagine.
Oh, yeah. This paper tackles the two big questions in multi-agent coordination. The first one is who to coordinate with, which boils down to figuring out which agents actually need to work together.
So figuring out the teams, basically.
Yep. And then the second question is how to coordinate. That's all about the nuts and bolts, the algorithms, the strategies, the mechanisms that make it all tick.
So it's not just throwing a bunch of AI agents together and hoping for the best. There's a real science to it.
Absolutely. And this paper connects all this theory to actual applications. It shows how multi-agent coordination is being used to solve real-world problems in robotics, transportation, even space exploration. It's mind-blowing.
It's like getting a masterclass in multi-agent coordination, all in one paper. Now let's unpack some of these concepts a bit, starting with coordinated learning. It seems like a pretty crucial piece of the puzzle.
Definitely. Coordinated learning is all about agents learning from each other's experiences. So they all improve over time, both individually and as a team, like a team of athletes training together.
Okay, so instead of each agent fumbling around on their own, they're sharing knowledge and strategies to learn faster and better.
Right. But you bring up a good point. Wouldn't all this sharing create a ton of data? Especially as the number of agents increases.
Yeah, that's what I was thinking. Could get overwhelming pretty fast.
Totally. And the paper dives into that. It talks about different ways to manage all of that communication and computation. Like there's fully connected learning where every agent talks to every other agent. And then there's sparsely connected learning where agents only communicate with a few close neighbors.
So it's like choosing the right communication channels for your team. You don't want to overload everyone, but you don't want information silos either.
Exactly. It's all about finding the right balance. The paper talks about techniques like MADPG, which is great for those fully connected systems, and then there's ComNet for those more selective, sparsely connected setups.
So finding the sweet spot between sharing enough and keeping things manageable.
Yep. And it's not just about how much information they share, it's about the quality. How do we ensure that agents are learning the right things from each other? That's where credit assignment comes in.
Credit assignment. Sounds like performance reviews for AI agents.
That's a great analogy. It's about figuring out which agent deserves credit when the team wins, and, importantly, who's responsible when things go wrong. This is how they learn from their mistakes and keep improving.
So it's like a continuous feedback loop, guiding their learning process.
Exactly. The paper mentions some cool techniques here, like MADPG, Coma, and IC3net. They all tackle this credit assignment problem in different ways, but they all point to just how complex coordinated learning can be.
We've been talking a lot about learning, but communication and cooperation are crucial in any multi-agent system, right? Not just when they're learning.
Oh, absolutely. Communication is like the glue that holds it all together. It's how agents share their goals, what they're seeing, and even what they're planning to do.
So like a team of explorers charting a new territory, they need to stay in contact, share their findings, and any potential dangers.
Exactly. And the paper goes really deep into the nuts and bolts of communication. Everything from communication topologies to encoding messages and different forms of communication. It's fascinating stuff.
Okay, let's start with communication topologies. What exactly are we talking about here?
So communication topology is all about the structure of the communication network. Who can talk to whom, basically? Like, are we using email, a group chat, or just shouting across the room?
So deciding on the communication channels for the team makes sense.
Right. And the choice of topology can have a huge impact on how well the system performs. It affects everything from how fast they reach a solution to how they handle failures.
So it's not just about whether agents can talk, it's about how they talk.
Exactly. The paper looks at a whole range of topologies, from fully connected networks where everyone can talk to everyone else, to more structured ones like rings or chains, and even dynamic topologies where the connections between agents change over time.
Kind of like choosing the right organizational structure for a company, right? A small startup might have everyone talking to everyone, while a giant corporation might need a more hierarchical approach.
Great analogy, and the paper makes it clear that there's no one-size-fits-all solution. The best topology depends on a bunch of factors like the number of agents, the complexity of the task, and how reliable you need the communication to be.
Okay, so we've got the who can talk to whom figured out, but what about the what? What kind of information are they sharing?
Well, it can be a whole range of things, from raw sensor data to high-level plans and intentions. They might share their observations, what they believe about the environment, their next move, or even things they've learned.
So it's like a group of detectives on a case, sharing clues, theories, and strategies.
Perfect analogy. But just like with detectives, AI agents can't always be completely open with each other. Sometimes they need to be strategic about what they share.
Like playing poker. You don't want to show your whole hand, but you need to give enough away to influence the other players.
Right. And the paper even mentions how the way agents encode their messages can be determined through evolution or learning, so they figure out the best way to communicate over time.
Kind of like people stranded on a desert island who don't speak the same language. They might start with gestures, but eventually they'll develop a more complex way to communicate.
Exactly. It's amazing how adaptability plays such a big role in all of this.
So we've covered who can talk to whom and what they're talking about. But even with all this communication, I imagine conflicts are bound to pop up, especially when agents have different goals or they're competing for resources.
You're absolutely right. Conflict resolution is a huge part of multi-agent coordination. And the paper dives into a whole range of mechanisms for dealing with those inevitable clashes.
Well, that sounds like a topic for our next deep dive session then.
It is. We've got a lot to unpack there.
All right, conflict resolution. Feels like we're talking about team dynamics here, but for AI agents, what happens when these agents have to share resources or their goals clash?
Well, imagine a swarm of robots zipping around a warehouse. They need to pick up stuff, move it around, and not crash into each other, all while trying to be as efficient as possible. Without good coordination, it's chaos. Robots bumping into each other, tasks getting stuck, the whole system breaks down. That's where conflict resolution steps in.
So it's like air traffic control, but for robots.
Exactly. The paper highlights a few key ways to handle these conflicts. One is path planning.
Path planning? So the robots plan their routes ahead of time.
Yeah. To minimize the chances of bumping into each other, think of it like GPS for robots, but they're not just avoiding traffic, they're factoring in each other's movements too.
So it's not just about each robot finding the shortest path. It's about finding paths that work well together as a whole.
Exactly. Then there's resource allocation. Like, what if there are only so many charging stations or limited processing power?
Right. They can't all charge at once.
Exactly. The system needs to figure out how to share those resources fairly and efficiently, so no one agent is hogging everything.
It's like that one coffee machine in a busy office.
Yeah.
You need a system to make sure everyone gets their caffeine fix.
Huh. Exactly. And the paper mentions some ways to do this, like scheduling algorithms. So agents take turns based on their priority or deadline, or auction mechanisms where they actually bid for resources.
So they're like little robot entrepreneurs.
Yeah.
But what about those split-second decisions, like if a collision is about to happen?
That's where behavioral adjustments kick in. Agents might need to stop, slow down, or change direction on the fly to avoid a crash, even if it means going off their original plan.
So like defensive driving, but for robots.
Precisely. And this is where things get really interesting. The paper explores different approaches to conflict resolution. There's centralized control, where one big boss makes all the decisions.
Top-down approach.
Right. But then there are distributed methods where agents make decisions on their own based on what they see locally and what they hear from their neighbors.
So more like a bottom-up approach.
Right.
With each agent having some autonomy.
Exactly. Centralized control can, in theory, find perfect solutions, but can be slow and clunky in a fast-changing environment.
It's not very adaptable.
Right. Distributed methods are more flexible, but they might not always find the absolute best solution.
Because they might not be perfectly in sync. It's like the classic debate between central planning and free markets. But for robots.
Yeah. It all comes down to the specific application and what trade-offs you're willing to make.
So, no easy answers there. Can you give us a concrete example of how this works in action?
Sure. The paper talks about something called the lexicographic convention. It's a pretty simple rule-based method for handling conflicts at intersections.
Okay, so picture two robots heading towards an intersection.
Right. The lexicographic convention basically says the robot with the lower ID number gets to go first. Simple, but it prevents crashes.
It's like a traffic light system, but based on seniority.
Exactly. It's all about establishing clear rules so everyone knows what to do. We've been talking a lot about the theory behind all this, but I'm curious to see how these ideas are being used in the real world.
Me too. Let's move on to some actual applications. Let's start with search and rescue. Feels like the perfect scenario for multi-agent systems.
Definitely. Imagine a disaster zone, too dangerous for humans to enter. You send as a team of robots to search for survivors, assess damage, and maybe even deliver supplies.
Like a high-tech rescue squad.
Exactly. But there are tons of challenges here. These robots need to coordinate their movements so they cover the area efficiently, no wasted effort, and they need to share what they find. Like, hey, I found a survivor over here, or watch out, there's a hazard up ahead.
So it's like a well-coordinated search party, but with robots.
Exactly. And they can't just be following pre-programmed paths. They have to adapt to changing conditions, make decisions on the fly, and even work with human rescuers.
It's a whole other level of complexity.
It is. The paper talks about how researchers are using algorithms to let robots form dynamic search patterns, like lines or V formations, and they can adapt these formations based on the terrain and what they're finding.
It's like a flock of birds, but with a life-saving purpose. Super efficient. What about other applications? Let's talk warehouse automation. That's a field where robots are already making a huge impact.
Oh, yeah. Warehouses are becoming more and more reliant on multi-agent systems to manage inventory and get orders out the door quickly and accurately. You know, think those massive Amazon warehouses, hundreds or even thousands of robots working together.
It's like a giant robot anthill.
Haha, that's a great way to put it. But these warehouse robots need to be incredibly coordinated. They need to avoid collisions in those narrow aisles, figure out the fastest routes, and even work together on tasks like lifting heavy objects.
It's like a perfectly choreographed dance, but with robots and packages.
Exactly. And it all has to happen in real time, with new orders coming in and inventory levels changing constantly.
So these systems need to be super adaptable. No time for rigid routines.
Right. And that's where the power of multi-agent coordination really shines. The paper highlights examples like Amazon Robotics and Kaineo smart warehouses, swarms of robots working together seamlessly to tackle super complex tasks. It's the future of logistics.
It's mind-blowing to see how far this technology has come. Okay, let's keep rolling with this transportation theme. We've got robots in warehouses, but what about our roads?
That's where things get really exciting. From traffic light control to self-driving cars, multi-agent systems are transforming how we move people and goods.
That's a whole other level of coordination. Let's dive into that next.
All right, transportation systems. This is where multi-agent coordination gets real. We've all been stuck in traffic, wishing things could move a little smoother. How are multi-agent systems helping with that? Well, think about traffic lights. Instead of each one just doing its own thing, imagine if they could talk to each other, coordinate to optimize the flow of traffic across the entire city. That's the idea behind multi-agent traffic signal control.
So, like a network of smart traffic lights, all working together to prevent those horrible gridlocks. How does that actually work?
Well, there are a bunch of different approaches. Some systems use decentralized control, where each intersection makes decisions based on the local traffic and what it hears from its neighbors. Others use reinforcement learning, where the agents learn how to time the lights better over time using real-time traffic data.
So it's like teaching a computer to play a citywide game of traffic Tetris, moving cars around to keep things running smoothly.
That's a great way to put it. And it can be much more adaptable than those old school traffic light systems that just have fixed timings.
Yeah, those can be a nightmare when there's an accident or a sudden rush hour surge.
Exactly. Multi-agent systems can react to things like that in real time, adjusting the lights on the fly to keep things moving. They can even use historical data to anticipate traffic patterns and adjust the timings preemptively.
So it's like having a traffic management system that can see into the future. That's pretty cool. But what about autonomous driving? That seems like the ultimate challenge for multi-agent coordination?
Autonomous driving is definitely one of the most complex applications, maybe the most complex. You've got to coordinate not just between the vehicles, but also with pedestrians, cyclists, and all the infrastructure around them.
It's like a real-life video game with constantly moving pieces all trying to get somewhere.
Exactly. And the stakes are incredibly high. We're talking about safety here, so even a small mistake can have big consequences.
No room for error.
Right. That's why the paper emphasizes the need to think about autonomous driving from a multi-agent perspective. It's all about vehicles communicating their intentions, figuring out right-of-way, and coordinating their movements so everyone stays safe.
It's like a perfectly synchronized dance, but with cars.
Yeah. And the paper goes into different approaches, like cooperative adaptive cruise control, where cars form platoons to save fuel and reduce congestion, and intersection management, where cars talk to each other, and the infrastructure to navigate intersections smoothly and safely.
It's pretty amazing to imagine a future where our cars basically drive themselves, all working together to create a more efficient and safer transportation system. But it does make you wonder about the role of humans in all of this.
Absolutely. Those are the big questions researchers and policymakers are trying to figure out as we move towards a future with more autonomous vehicles on the road. And the paper talks about how human-machine interaction is going to be key. We need to make sure humans and AI can work together smoothly and safely.
It's a good reminder that even as we develop more and more advanced AI, the human element is still crucial. We need to make sure these systems are designed to work with us, not replace us.
Exactly. Okay, ready to shift gears a bit. Let's talk about humanoid and anthropomorphic robots.
Humanoid robots. You mean robots that look and act like humans?
Yep. They present unique challenges and opportunities for multi-agent coordination. Think about a robot working in a home or a factory. It needs to be dexterous, adaptable, and able to collaborate with humans. Lots of coordination required.
Yeah, I can imagine.
The paper stresses the importance of multi-agent approaches for these robots. You basically treat each limb, sensor, or subsystem as its own agent. They all communicate and coordinate to make sure the robot functions as a whole.
So it's like the robot has a whole team of mini robots inside, all working together.
Right. And this approach can lead to some pretty amazing robots. Robots that are more adaptable, resilient, and even creative.
Creative robots, that's kind of scary, but also super cool.
The paper gives examples like dual-arm robots, where two arms work together to handle objects, and even dexterous robot hands with multiple fingers that can grasp and manipulate things with incredible precision.
It's wild. I can see these robots helping us with all sorts of things in the future, from surgery to manufacturing to even caring for the elderly.
Definitely. But, like with any powerful technology, we need to be thoughtful about the societal impacts. The paper highlights the need to make sure these systems are designed and used ethically and for the benefit of humanity.
Makes sense. Okay, let's blast off to our final destination, space. Satellite systems seem like a natural fit for multi-agent approaches. They're already distributed and working together up there.
Absolutely. Think about a constellation of satellites providing communication coverage, monitoring the weather, or even exploring other planets. They all need to coordinate perfectly to make sure there are no gaps in coverage, performance is optimized, and they can adapt to the ever-changing conditions of space.
It's like an orchestra of robots orbiting the Earth, each one playing its part.
A cosmic symphony. One of the biggest challenges is maintaining that continuous coverage, especially with those satellites that aren't in geostationary orbits. They're constantly moving, so you need to make sure there's always a satellite in the right spot to provide uninterrupted service.
That sounds like a logistical nightmare.
It is. But that's where multi-agent systems come in. The paper talks about techniques like orbit optimization, collision avoidance, and communication scheduling. They all help the satellites communicate their positions, adjust their orbits, and work together seamlessly.
It's pretty amazing to think about these robot swarms operating autonomously in the vastness of space, coordinating their actions to accomplish these complex missions.
It really shows the power of multi-agent systems to solve problems that would be impossible for a single satellite or even a traditional centralized control system.
Okay, ready for our last stop on this deep dive. This one's cutting edge. We're talking LLM-based multi-agent systems.
LLMs.
Yes.
It's large language models that everyone's been buzzing about. What do they have to do with multi-agent systems?
Well, LLMs are changing the game for AI, right? They can understand and generate human language, they can reason, and they can even learn from their interactions with us. So researchers are starting to use them to create even more powerful agents. So we're talking about agents that can communicate like humans, work together on complex problems, and maybe even come up with solutions we haven't even thought of.
Exactly. The paper talks about how these LLM-based agents are being used for things like decision-making. Imagine a team of agents, each one specialized in a different field, working together to tackle a huge challenge, like climate change or finding a cure for a disease.
It's like having a global brain trust at your fingertips. And they can not only process information, but explain their reasoning, brainstorm ideas, and even have meaningful conversations with us.
Exactly, and that's just one area. The paper also talks about using LLM-based agents for behavior simulation, like creating realistic simulations of human behavior, social interactions, even entire societies.
That's mind-blowing. It's like creating a virtual world populated by AI that's almost indistinguishable from real life.
Right.
It's pretty exciting, but also kind of makes you think about the implications.
For sure. Like with any powerful tech, we need to be cautious and think about the ethics. The paper talks about that too, emphasizing the need to make sure these systems are used responsibly and for the benefit of everyone.
It's been an incredible journey exploring the world of multi-agent coordination. From the basic ideas to all these mind-blowing applications, it's clear this field is going to change how we solve problems, interact with the world, and even understand ourselves.
I totally agree. This paper was a fantastic overview of the challenges, the opportunities, and where this whole field is headed. Anyone who's curious about the future of AI needs to check it out.
Thanks for walking us through it all. It's been a fascinating conversation. And to all our listeners, keep exploring and keep pushing the boundaries of what's possible with multi-agent systems. Until next time, dive deep.